So my name is Ezra Gordon, and I'll be talking about the chemistry of global literacy, and I'll be going into depth on paper, ink, and socioeconomics. Let me just get the So first I'll overview how my presentation is going to look. So I'll have my thesis, which kind of discusses my results. And then I'll look at the history of writing technologies and how they've affected literacy. And then I'll look for how chemistry has recently affected literacy and how it will continue to do so in the coming decades, hopefully. And of course, we're doing all this with the lens of AP chemistry level science. So my thesis is, as methods of synthesizing common materials have come to include more chemical techniques, the role of chemistry in increasing global literacy has grown significantly, and this will continue to the future as chemistry opens new opportunities for spreading access to literacy more effectively. And I'll kind of explain this meaning better. So first, we're going to look at the history of paper. So it starts in Egypt and other ancient civilizations with papyrus and parchment and other rather cost-ineffective methods, right, where you kill cows. You want to write a story about, I don't know, a cow, let's say. So it's not that story. So then around 1000 BCE, you get the development of wood pulp paper in China. And it's obviously lower quality than what you'd see today, but it is the same historical product. So then during the explorers' age and Renaissance, that's moved to Italy, and the process is further refined. And then eventually you get global use of refined paper as we see it today. And that's what I'm going to zoom in on for the chemistry discussion. So just to go over the chemical structure of paper is polymers, which are long strings of molecules repeated over and over again. And there are both good and bad polymers in wood. And the good ones are the ones that you want in nice, clean, white paper. And the bad ones will mess with the color or the consistency or its integrity. So again, the good is cellulose, which is sugar molecules over and over again. And the bad ones include lignin and hemicellulose. So the question then is, how do you get from plant cells, and more specifically their cell walls, with these polymers to pure paper? So again, I think ancient civilizations tried asking nicely, and that didn't work out for them, and they're all dead now. So we use chemical synthesis. So I'm going to zoom in on a very specific part of the process called sulfite pulp. So just to kind of describe the issue here, if I give you a knot of two colors of string, say red and blue, and I said, please give me only the blue knot and without any red left, and I made this ball really small and really complicated, you would have no clue where to start, and you wouldn't have any good way of going to do this. But if I hand you a pair of scissors and I say, here, you can cheat a little bit, that makes it a whole lot easier. So what this sulfite process does is it gives us the chemical scissors necessary to remove this bad polymer, and we can keep the cellulose, which are those straight molecules that we want. So here is a zoomed in bad polymer. So, and this is where we will snip with our chemical scissors. So by combining sulfur and oxygen like we breathe and water like we drink, you get what's called sulfurous acid. And this is sort of similar to what Sam was talking about. And this acid will react with the polymer by breaking these bonds with the oxygen between carbons, which are called ether bonds. And it'll basically just snap the bonds apart, and you'll end up with this long red string that we don't want into little pieces of red string that will just kind of fall out and can be separated easily. So this process ensures that you get a high quality, long lasting, cheap paper, which means that you can spread the written word globally at a fraction of the cost of what it would have been even 100 years ago, but definitely 1,000 years ago. And this will help to continue to spread literacy. And although it's not a permanent solution, it definitely removes roadblocks that we would otherwise encounter. So now I'm going to go through a similar process with ink. So again, we have ancient civilizations that use rather rudimentary techniques. So they extract carbon from burnt oil, like from a lamp, and they would put that into an ink. Then you have the development of India ink in also use carbon, but from burnt bones, actually. Then, during the Dark Ages, you have the development of what's called iron gall ink, which are from these growths on oak trees that you mix with organic acids to get a good, lasting dark wood. That's what you see was used to write the Declaration of Independence and Pride and Prejudice and a lot of famous works during the Renaissance and Enlightenment, and then obviously nowadays you have modern synthetic inks which still use organic dyes but are much more complicated in nature and are used globally. And once again, this is what we're going to focus in on. So the chemical structure of dyes is a pigment or dye, which will depend on what we're using. So again, I said people use carbon, and now we use these middling sized molecules. And then you have a solvent, which makes the ink actually write well and stay on the paper and not clog your pen and give you the kind of final coloring and spreading of ink on your paper that you want. So that will include waxes, lubricants, surfactants, and drying agents. And all of those give you kind of the right ink that you want when you're writing and not sort of a clunky mess in your pen that you can't do anything with. So I'm just going to zoom in on the synthesis of one surfactant because it's a very complicated process. And so the idea of a surfactant is that you have one polar end and one non-polar end. You can think of this in terms of soap, where if you're washing your body with water, but the grime on your skin is oil-based, then you need something that's going to connect the oil to the water so it can wash off. So a surfactant will do this, and it will basically enable the water to actually get rid of oil, even though water and oil don't mix. So with this mess of chemicals, we're just going to look at the synthesis of glycerol, which, as you can see, it has these oxygens and hydrogens, which are the polar part, and it has this carbon backbone, which is the non-polar part. So you make this through a process called saponification, which literally means soap making, and you combine with what's called a triglyceride, which is a fat like Crisco or lard or something like that, and sodium hydroxide, like you would find in our lab next door, and you use in titrations as a base. So the sodium hydroxide literally snaps off the ends of the molecule, and you end up with this both polar and non-polar molecule. So again, with these cheap processes, with inks that last and are easy to read and can travel long distances and so on, you can get more books written, and more, that means more people have access to written materials, and that means more people can learn to read. But now I'm just gonna sort of put my money where my mouth is with these slides, because I've been saying lots of big words, and I've been saying that look, oh, chemistry is the best thing in the world, but here's sort of evidence of that. So this is a graph of estimated literacy percentage in the world by year. And as you may have guessed, in 700 CE, no one cared what the literacy percentage was, so no one was taking data. But I used data from how many manuscripts were published and how many books were written during different time periods, and adjusted for world population to get an estimated graph during that time. But there is still an issue with this graph, which is that it's curving upward, and that's all fun and good, but it's hard to tell where there are important curves in the graph because of it. So let's say there is a person, and that person knows how to read. So if that person, say, teaches their 2 kids how to read, and 2 is just an abstract number, but if we assume it's some number like that, then their kids will teach their grandkids how to read, and that becomes 4 people. And in theory, that would continue to 8 people and 16 people, and so on. So in theory, for literacy, you should get an exponential growth that grows in proportion to itself. So that means that looking at the graph as we had it isn't actually a good method if you want to get to see what's meaningful. So instead we use a log graph, because here, if we had the expected growth, we would just get a straight line, something like that, as literacy spreads from 1 to 2 to 4 people. So here you can see a lot more of what's going on and what's unexpected, more importantly. So here, with this first jump, is when you have the invention of iron gall ink during the Dark Ages, which was the newest, hottest technology for writing long-lasting documents. And again, you can still find documents written 500 years ago today with this technology. This little jump right up here is when you have printing ink invented. So this is with the printing press. But, I guess Gutenberg gets a lot of credit, but there's also the fact that you need to get a special ink that will stick in a sufficient amount to your wood blocks, your movable type, but it'll also stick to your paper and stay there indefinitely. Now, this last little uptake here is when you have the development of the sulfite process and also other modern synthesis processes like the craft process and other things you would see in industrial scale manufacture of ink or paper materials nowadays. So you can see whenever we have these jumps, you have corresponding developments in writing technology that help spread literacy. So far I've been talking a lot about innovation, but I interviewed English teachers, and English teachers didn't really care in the least about innovation. What they said it was much more about was access. That's one of the English teachers I interviewed. And access is much more important, because nowadays, books are cheap, and ink in the quantity you would need is cheap. And so the fact is, there's still 20% of the world they can't read. So access is what's really preventing people at this point. So I'm going to talk about a few issues that chemistry can solve with regards to access to learning. So the first one is about nutrition, sort of like Gummer discussed, or Ed discussed. And this is very tuned into vitamin A, or as nerds call it, beta carotene. So the vitamin A obviously is an essential nutrient, and vitamin A deficiency is a huge problem in developing countries. As you can see, hundreds of millions of people suffer from it, and it can include its effects and issues associated with it include immunodeficiency, blindness, and death. And a lot of studies have shown that blind and dead people really struggle to learn how to read. So one solution to this is biofortified crops. So when you hear about biofortification of crops, what you should think about is that they're genetically modified organisms with added nutrients. So there is sort of a knee-jerk response that GMOs are bad and can have associated risks, but the GMOs that have been used to help give these micronutrients to people in developing countries have been properly tested and created in a safe way. So this one that you see here is called golden rice, and it was developed to have vitamin A in a high amount, and that gives it its golden color. And this is more like vitamin A heavy, I guess you could call it, than any fruit or vegetable you would find naturally. And it means that these hundreds of millions of children can now get the necessary nutrients so that they can see and attend school for a very low cost. The company that made this distributed it for free in developing countries. And just note, back on the GMO note, we humans have been selectively breeding crops for 10,000 years, and that's where you see corn developing into what it is today. Just with new technologies, it means that we can do it in 3 years instead of 3,000 years, and that we can get these poor children to read in 3 years instead of 3,000 years. Second issue is called period poverty. So hundreds of thousands of girls don't have access to proper hygiene products for their periods. And this seems like sort of a non-literacy related issue, but actually it's very related, because these girls are missing a week of school once a month because they can't come to school out of shame or discomfort and issues like that. So if that's half the population and that's a quarter of the time, then that's more than 10% of school is just not happening for these girls, or for these areas. So the solution is a man by the name of Padman. So this is Padman here. He is an Indian man who developed a cheap technology for pads that cost 1/10 of their market value in these countries. And he's distributed this technology with a machine that costs 1/100th the price of a similar machines in industry to give thousands of women access to hygiene products that will enable the girls to go to school. Now, an interesting note here is I was talking earlier about the lignin and cellulose in paper, and he actually also uses wood pulp, but he uses a process called thermomechanical pulping. It means he doesn't actually remove the lignin, which for him is good because it helps with the absorbance and the rigid structure of the wood, which is not what you want for paper, but it is what you want for a hygiene product. So, third issue I'm going to talk about is access to digital materials. And I'd say this one is the least pressing, and the solution is not as good as the other one, but it's still important. So, as you see, even at Weston High School, technology is a huge growing industry in classrooms, right? All four of us have computers that we bring to school, and we use it to write our essays and to take notes sometimes and to watch, or to get materials. If you're in a developing country, there's no chance that every classroom is going to get access to an iPad or a computer, and much less every kid. So the solution to this in the future could be what's called e-ink, electronic ink or electrophoretic ink. So electronic ink uses tiny ink capsules, and this is where the chemistry comes in instead of just not chemistry, other unimportant topics. You know, this is where the cool stuff comes in. So they use charged ink capsules to make dyes come to the surface or go down within a screen. Now, the reason this is useful is because the screens we're looking at right now, well, I guess not the projectors, but the screen I'm looking at right now uses LED lights to project, and that takes a lot of energy. For these ink capsules that you see, once you change the state to be black or white or red or yellow or cyan or magenta, it will stay that way until you apply a new charge, which means that it doesn't take any energy at all to change what you see on the screen. This is sort of like an old-fashioned Kindle if you've seen one. And another important advantage of this is that unlike this, an LED screen, this is not susceptible to glare. So if you don't have a classroom and you're in a place that gets a lot of sun, you can still read these screens because they actually have pigment on the screen that's reflecting light rather than something shining light that has to compete with the sun. So with these decreased need of electricity and the decreased need of shade or sufficient brightness or energy, these could be very reasonable solutions to giving access to digital materials to people in developing countries. And one more thing that I would say is that chemistry is not fully equipped to deal with all the issues of literacy. So there are some barriers that I discussed with English teachers that chemistry can't deal with. So Mr. Kelly noted that language barriers are a big thing. There are over 1,000 written languages in Africa that people still speak, that people use. So there's no conceivable global system that could have every single language accounted for that you're teaching. Another issue that Mr. Henry mentioned was cultural barriers. If learning to read is not a priority for you, then good luck trying to have these people learn how to read, right? So you can argue that the problem is kind of solved itself. If someone doesn't learn how to read, don't force them to read. But if you have a generational barrier where kids want to learn to read and their parents don't, or if you have a disaster that you need people to have access to written materials in a pinch, I guess, having these people learn to read could still be an advantage. And one more thing is that Ms. Link mentioned was access to qualified teachers. So I'm lucky to have a very qualified teacher in my school, or at least there are dozens really. But if you have these villages where very few people don't know how to read, it's a self-feeding cycle, right? So you can't find a teacher, so you can't teach the students, so no one's there to teach, so you can't find a teacher, and so on. And this is a big issue. And none of these things have immediate solutions with chemistry, obviously. With chemistry as we know it, I guess I can hope that one of us will invent something that fixes this, but for now, we're stuck at here. So, thank you so much.